Everyone, my name is Mark Miller, and today I'm going to be going over the first law of thermodynamics. And this is one of the main laws that we use in thermodynamics in order to solve problems. So, the first law of thermodynamics is the change of the total energy is equal to heat minus the work. And so, the total energy is also a summation of kinetic energy plus potential energy plus internal energy. And over to the right of the paper, we have a schematic of a system, a closed system, in which the first law of thermodynamics applies, where we have heat going into the system. The dotted line shown here is the boundary of the system, and we have work going out of the system. And so again, we have the first law of thermodynamics, delta E equals Q minus W. Now, delta E is a property, and so the property is process independent. So the state of the system at the final and the state of the energy at the initial do not depend on the process. However, Q and W are not properties, and thus are process dependent. And so this is a very important rule when we have delta E equals Q minus W. And so next, how are we going to utilize first law of thermodynamics for certain cases? So the first case we have here is for quasi-static and reversible processes. Now, a quasi-static process is a process that moves so slow in which thermodynamic equilibrium is met throughout each interval. And these equilibrium states are very close together, so it could be considered quasi-static. And a reversible process is a process in which the process can be reversed and still yet be physically possible. Now, in real cases, no process is truly reversible, but this is for one of the assumptions in order to solve problems. It's a valid assumption. And so for an equation for work that we have for quasi-static and reversible processes is work equals the integral from V1 to V2 of pressure times dV, which is for volume. So it's the integral with respect to volume of the pressure, and that's equal to work. Next, we have incompressible liquids and solids. And before we get into incompressible liquids and solids, we have to talk about specific heat, whereas CV is a specific heat at a constant volume, and CP is a specific heat as a constant pressure. And these are just properties of these are just scientific properties of the material that we're dealing with within systems. So this is just specific heat. Now, for incompressible liquids and solids, pretty much with volumes constant, we have CV equals CP. And so this we're just going to denote this as C. And we have delta U, which is the change in internal energy, equals MC delta T. So this will be mass times specific heat times temperature at the final state minus temperature at the initial state. And so this will be delta U. Finally, we have open systems, in which we have mass flowing in and out of a control volume. Control volume is a set volume in time, and mass flows in and out, this boundary here throughout time. And as mass flows in and out of this boundary, we have work and heat that are both generated within the boundary. And we want to calculate how heat and work are related to the mass flux within the control volume. And so we want to create an equation for the first law of thermodynamics for an open system. So this is what we're going to do here. So we have dm dt is going to equal, which is the change of in mass with respect to time, is going to equal m dot I minus m dot E. So this will be the mass flux into the control volume minus the mass flux out of the control volume. And at steady state, this is just a conservation of mass equation. At steady state, dm dt equals 0. Thus, the mass flux into the control volume equals the mass flux out of the control volume. And this is going to just equal m dot. And m dot, and again, the dot above the letters is just a notation for the derivative with respect to time. And so we have q dot and w dot here. So this is going to be the powers of the heat and the work that is generated within the control volume. So this is going to be the work with respect to time and the heat with respect to time. Next we want to define what m dot is, and m dot exactly equals rho VA. So this will be the density times the velocity times the area times the cross-sectional area through which the mass flows. And so that's how you formally define m dot. Next we have specific enthalpy, which will equal specific internal energy plus pressure times a specific volume. And so this is an important equation because everything is normalized by mass. And this is what we want to use when we're dealing with mass flux within a control volume. So we have H over M equals U over M plus PV over M. So this will be the same thing here, where we denote lowercase letters to denote specific values. And finally, we derive the first law of thermodynamics for open systems. So we have dE dt, and the CV's subtitle is for the control volume, where we have dE dt plus m dot E, which is the mass flux exiting the control volume, times the specific enthalpy plus 1/2 the velocity exiting squared, so this will be the kinetic energy term, plus GZE, which is your potential energy term, minus m dot I, which is the mass flux out, HI, specific enthalpy in, plus 1/2 VI squared, which is the kinetic energy term into the control volume, plus GZI, which is the potential energy, and that equals Q dot minus W dot. And so this will be the derivative with respect to time of the heat minus the derivative with respect to time of the work. And so this is the first law of thermodynamics for open systems. Next we have an example, and we're going to be doing an example from the book. So given, a cutting tool uses a nozzle that generates a high-speed jet of liquid water, TW equals 20 degrees Celsius. Assume an exit velocity of 500 meters per second with a jet diameter of 2 millimeters at steady state. And we want to determine the mass flow rate of the liquid water flowing through the nozzle, and we want to determine the pump power required to generate this water jet from a steady supply of 20 degrees Celsius liquid water at rest. Assume the specific enthalpy of the water at the inlet of the pump and at the exit of the nozzle are the same. So first we want to make a schematic of the system, where we have the boundary of the system shown here with these dotted lines. And we have this pump, which is going to be our control volume, where we have mass flux into the control volume and mass flux out of the control volume. And this pump is going to generate work and heat. But however, we know that pumps are adiabatic, and so this Q term is going to equal 0. Next, and we have this coming from a steady supply of water. So this is a schematic of our system that we're going to be used to solve for the work of the pump. Next, we have to create an engineering model. So this is just going to be all the assumptions we make in order to successfully solve this problem. So we know that this system is an open system through which mass flows. We know that this system's at steady state, so dECV dt equals 0, and m dot is constant. We know that the change in potential energy is 0, since the change in height throughout the pump is 0. We know that the pump is adiabatic, so Q dot equals 0. And we know, given in the problem statement, that the specific enthalpy exiting the nozzle is equal to the specific enthalpy entering the pump. And so now we get into solving the equation. So for part A, we know that m dot equals rho VA. And so we know all of these terms here. We have the density, the velocity, and we know that the area is equal to pi d squared over 4. And so we just plug in all of these terms here, and we get our final m dot term to be 1.571 kilograms per second. And second, we just need to utilize the first law of thermodynamics in order to solve for the work. So we have m dot, which is constant, 1/2 VE squared plus GZE plus HE minus 1/2 VI squared minus GZI minus HI, and that equals Q dot CV minus W dot CV. So we know that the potential energy is zero. Thus, we have this term and this term equal to zero. We know that HE and HI are the same, so they both cancel out. We know that the water is starting from rest, so the initial velocity is going to be zero, and we know that the pump is adiabatic, so Q will be zero. Thus, this really simplifies our equation to make W dot CV, which is the power of the pump, equals negative 1/2 M dot VE squared. And we know all these terms, so negative 1/2, 1.571 kilograms per second, times 500 meters per second squared, and this is going to equal negative 196,375 watts, and also be simplified to negative 176.375 kilowatts. So this is ultimately how do you utilize the first law of thermodynamics to solve for an open system, and that's pretty much it. If you have any questions, let me know. Thank you.